Hello and welcome to General Astronomy, Lecture 24, The Formation of a Protostar. Our ancestors imagined the stars as fixed and permanent, but this seeming permanence is an illusion that occurs only because human lifetimes are so short compared with stellar lives. By carefully observing stars and their surroundings, we have unlocked the secrets of the life cycles of stars. In this lecture and the next, we will see how and why interstellar gas clouds collapse and give birth to stars, examine the processes that make star births surprisingly violent, and discuss why stars can have masses only within a particular range. Star formation is actually a common process. Counting the number of young stars in our region of the galaxy suggests that an average of 2 to 3 stars are born somewhere in the Milky Way galaxy every year. We see the birthing grounds of those stars with our own eyes whenever we look into the Milky Way on a dark night, like you see in this image. The black patches within the Milky Way, which you can see in the band here, going from kind of the center on the left to the top right, are interstellar gas clouds that appear dark because they block our view of the stars behind them. These gas clouds provide the raw material for star formation. We often think of space as being empty, and it is indeed a superb vacuum by earthly standards. However, space is not completely empty, as we find at least some gas and dust is found everywhere that we look. We refer to the gas and dust found in the space between the stars as the interstellar medium. The gas between stars is composed mostly of hydrogen and helium. Hydrogen and helium were the only chemical elements produced in the Big Bang. The very first stars must have been born from clouds made of this hydrogen and helium gas. Since that time, stars have transformed a small fraction of the original hydrogen and helium into heavier elements. Any interstellar cloud is called a nebula, or nebulosity, and for plural you say nebulae. You can see evidence for the interstellar medium with the naked eye. Look carefully at the constellation Orion, like you see in the image here in the center. While most stars appear in the constellation as sharply defined points of light, the middle star, which I've boxed, is Orion's sword. Orion's sword, has a fuzzy appearance. This star is not actually a star at all, and in fact, if you zoom in on it, you find the Orion Nebula, a cloud in interstellar space. And this just happens to be one of the most common images of anything in space, really. It's a nearby, relatively speaking, image that we can pretty much get an image of quite easily, even with some of the more simple telescopes. Maybe not to this much detail, but still. So this is Orion's Nebula, and notice, even without much resolution, it might look like another star. But with higher resolution and better telescopes, we're able to figure out that this is not just a star, it is a region in space where it's just a bunch of gas and dust collected into one region. So let's learn a little bit about these clouds. The Orion Nebula emits its own light, with the characteristic emission line spectrum of a hot and thin gas. For this reason, it is called an emission nebula. Typically, emission nebulae have masses that range from about 100 to 10,000 solar masses. Emission nebulae are found near hot, luminous stars of spectral type O and B. Such stars emit copious amounts of ultraviolet radiation. When atoms in the nearby interstellar gas absorb these energetic ultraviolet photons, the atoms become ionized. Indeed, emission nebulae are composed primarily of ionized hydrogen atoms, that is, free protons and electrons. Astronomers use the notation H1 for neutral unionized hydrogen and H2 for ionized hydrogen, which is why emission nebulas are also sometimes called H2 regions. These H2 regions emit red visible light when some of the free protons and electrons get back together to form hydrogen atoms in a process known as recombination. Now, the technical side of all that isn't super important. The main idea here is that these are emission nebulas, in other words, they give off their own light because of the hot O and B type stars that are giving off lots of energy to excite the atoms around them and cause them to glow in this reddish light. So that's the basics of these emission nebula. But there are other types. The other evidence for dust is in the bluish haze surrounding some stars and sets of stars. A haze of this kind, called a reflection nebula, is caused by fine grains of dust in a lower concentration than found in a dark nebula, which we'll talk about in a moment. The light that we see coming from the nebula is starlight that has been scattered and reflected by these dust grains. The grains are only about 500 nanometers across, no larger than a typical wavelength of visible light, and they scatter short wavelength blue light more efficiently than long wavelength red light. Hence, reflection nebula have a characteristic blue color, much like our sky has a blue color in the daytime because the blue light is scattered. We previously discussed how a similar process, I just said this, excuse me, the scattering of sunlight in our atmosphere gives rise to the blue color of the sky. So it's a similar process. The third type of nebula is the most important for our discussion in this lecture and the next. There exist larger bits of matter called dust grains in the interstellar medium. These dust grains make their appearance in dark nebula and reflection nebula. A dark nebula is so opaque that it blocks any visible light coming from the stars that lie behind it. Now you can actually see that in this image here on the right. It's not just some void in space where there's no stars. There's just a big dense cloud sitting there that's blocking the light from behind it. So there are still probably just as many stars in this region as there are anywhere else. It's just light being blocked. These nebula have a relatively dense concentration of microscopic dust grains, which scatters and absorbs lights much more efficiently than single atoms. Dark nebula are typically many light years deep, such that they block the passage of light. In the same way, a sufficient depth of haze in our atmosphere can make it impossible to see distant mountains. So kind of think of fog. A very dense cloud of fog will block your view as you're driving, much like this here. Other relatively small, nearly spherical dark nebula are known as Bok globules, after the Dutch-American astronomer Bart Bok, who first called attention to them in the 1940s. A Bok globule resembles the inner core of a dark nebula, with the outer, less dense portions stripped away. A typical Bok globule is about 1/10 as large as a dark nebula. The density of the gas and dust within one of these Bok globules is indeed quite high, in the range from 100 to 10,000 particles per cubic centimeter. By comparison, most of the interstellar medium contains only 0.1 to 20 particles per cubic centimeter. So we're talking hundreds to tens of thousands of times more dense than the rest of the interstellar medium. So here's a wonderful image, really just a pretty picture I wanted to show you, but it has basically all three types of these nebulas in one. This is NGC 6188. It's an emission nebula, as you can tell by the pink, located about 4,000 light years away in the constellation Aura. The bright open cluster, NGC 6193, visible to the naked eye, is responsible for a reflection nebulosity within this region. So here you can see the cluster, and you can see the blue color because it is light being reflected off of these bright stars. NGC 6188 is a star-forming nebula and is sculpted by the massive young stars that have recently formed there. Some are only a few million years old. This spark of formation was likely caused when the last batch of stars went supernova, something you'll learn about very soon. So you can see the dark regions too, right? The very dense regions, especially like in these little appendages here. Those are all like Bok globules / dark nebulas. So this image really shows all three types of nebula in one. The pink emission nebulas, the blue reflection nebulas, and the dark nebulas or Bok globules. Stars form when gravity causes a molecular cloud to contract, and the contraction continues until a central object becomes hot enough to sustain nuclear fusion in its core. This is a bit of review as we talked about the birth of our solar system, but now we're going to apply it to all star systems. However, the role of gravity is only part of the story. For a more complete understanding of star formation, we must also pay attention to how gas pressure resists gravity. As we've learned, our sun remains stable in size because the outward push of the gas pressure balances the inward pull of gravity, a balance that we call hydrostatic equilibrium. The gas pressure is far weaker in the low-density gas of interstellar space, but so is the pull of gravity. In most places within our galaxy, gravity is not strong enough to overcome the internal pressure of this interstellar gas, which is why star formation does not occur everywhere. This means that stars will most easily form in regions where the interstellar material is relatively dense. So the atoms and dust grains are close together and the gravitational attraction is enhanced. To assist star formation, the pressure of the interstellar medium must be relatively low. This means that the star-forming region of the interstellar medium should be as cold as possible because the pressure of the gas goes down with temperature. So the only parts of the interstellar medium with that high enough density and low enough temperature for stars to form are the dark nebulas, or Bach globules. So you need a low temperature, so there's not a lot of pressure because of things bumping into each other and moving around, but you also need it to be dense, so you have a lot of material packed into one region so gravity can assist formation. So we only see that in the dark nebulas and Bach globules. Once gravity dominates a cloud within a dark nebula, the cloud will begin to contract. This is a bit of a review now. The contraction of the cloud gives gravity a growing advantage in the battle against pressure, which in turn means that a smaller total amount of mass is necessary for gravity to win the battle. Because these clouds are turbulent and lumpy, there are plenty of small, dense clumps within a contracting cloud that are soon able to shrink on their own. So you're seeing this here in a simulation on the right. Here's just a simulated cloud out in space. As it starts to collapse, it kind of clumps up in certain regions. It's not a perfectly symmetric process. So a large cloud therefore splits into numerous individual cloud fragments. Because dark nebulae contain many solar masses of material, it is possible for a large number of stars to form out of a single nebula. Thus, we can think of dark nebulas as stellar nurseries. So this simulation begins with a turbulent gas cloud, 1.2 light years across, and containing 50 solar masses of material. Random motions in the cloud cause it to become lumpy, with some regions denser than others. If gravity can overcome the thermal pressure in these dense regions, they can collapse to form even denser clumps of material. The larger cloud therefore fragments into many smaller lumps of matter corresponding to the bright yellow regions in the image. Each lump can go on to form one or more new stars. A cloud fragment will continue to collapse on itself as long as it remains cold, and it can remain cold as long as the photons emitted by molecules within the cloud can carry away the energy released by the contraction. It's easy for photons emitted by molecules to escape from the cloud early in the process of contraction, while the cloud's density is still low, because the photons are unlikely to run into other molecules after they are emitted. This situation begins to change, however, as continued contraction packs the cloud's molecules closer together. Cloud contraction makes it increasingly difficult for emitted photons to escape, because the growing density of the cloud increases the chances that a photon on its way out will be absorbed, leaving the absorbing molecule in an excited state. Collisions between the excited molecules and other molecules can then change the absorbed photon's energy back into thermal energy, which prevents it from escaping the cloud. The central region of the cloud fragment eventually grows dense enough to trap all of the radiation inside of it. When that happens, the inner regions of the cloud no longer radiate away their heat. The central temperature and pressure then begin to rise dramatically, and the rising pressure pushes back against the crush of gravity, slowing that contraction. This change marks the first stage of star formation. The dense center of the cloud fragment is now what we call a protostar, which is a clump of gas that will become a new star. Protostars look star-like, with surface temperatures and luminosity similar to those of true stars. However, a protostar is not yet a true star because its core is not yet hot enough for nuclear fusion. A protostar's mass continues to grow as more and more material falls onto it. This rain of mass onto the protostar continues until the gas surrounding the protostar is gone, either because the gas runs out or because something blows away the remaining gas. The star itself can blow away the surrounding gases through the combined effects of radiation and stellar wind, much as the sun's radiation and solar wind are thought to have cleared out excess gas during the formation of our own solar system. Observations show that young stars tend to have strong stellar winds, lending support to the idea that they can blow gas out of the solar system. In this image, we see a curved structure around a forming star. You can see that right here. It shows that the bright young star outside the lower right of the frame is blowing gas past this new forming star and possibly strips away the gas that has not yet fallen onto the new star. So off to the side of this image, we have some young new stars. They're very bright and they blow a lot of energy away. So as a result of that radiation and stellar wind, this new forming star nearby is being bombarded with it. So it's basically stripping away that material that could form this star. And as a result, it may never form to be a true star, or it will be less massive than it would have been otherwise. So far, our description of star birth may make it sound like the gravitational equivalent of squishing a piece of paper into a tight ball. However, observations of young stars show that their births can be quite violent. Now, this is a bit of review again, but it's important. Random motions of gas particles inevitably give a gas cloud some overall rotation, although it may be imperceptibly slow. However, as the cloud contracts in size, the law of conservation of angular momentum, as we discussed before, ensures that the rotation will become much faster, much like a figure skater bringing in their arms. This rapid rotation prevents gas from raining directly down onto a protostar. Instead, it settles into a protostellar disk, similar to the spinning disk of gas from which the planets in the solar system formed. Individual gas particles in the disk obey Kepler's laws, just like anything else that orbits a massive body, which means that gas in the inner parts of the disk move faster than gas in the outer parts. Because of these differences in orbital speeds, gas in any particular part of the disk rubs against gas that is slower moving with a slightly larger orbit. This rubbing generates friction and heat in the same way that rubbing your palms together makes them warm. This friction slowly causes the orbits of the individual particles to shrink until the gas particles fall onto the surface of the protostar, thereby increasing the protostar's mass. Because the process in which material falls onto another body is called accretion, a disk in which friction causes material to spiral inward is often called an accretion disk. And in fact, I actually studied accretion disks for my master's thesis. I studied it around a certain type of star that we might get to toward the end of our lectures. Observations show that many young protostars fire high-speed streams of gas, or what we call jets, into interstellar space. We generally see two jets shooting outward in opposite directions along the protostar's rotational axis, a phenomenon called bipolar outflow. Sometimes the jets are lined with glowing blobs of gas, which are presumably clumps of matter swept up as the jets plow through the surrounding interstellar medium. These glowing regions are called Herbig-Haro objects. So let's take a look at some of these. Here's a wonderful image. So this is a close-up of the Carina Nebula, which shows two Herbig-Haro objects, HH901 and HH902. You can see them here. Oh, excuse me, I zoomed in on it and went too far. The NASA and European Space Agency Hubble Space Telescope captured this billowing cloud of cold interstellar gas and dust rising from a temporous stellar nursery located in this Carina Nebula, 7,500 light-years away in the southern constellation of Carina. This pillar of dust and gas serves as an incubator for new stars and is teeming with new star-forming activity. Hot, young stars erode and sculpt the clouds into this fantasy landscape by sending out their thick stellar winds and scorching ultraviolet radiation. So again, you can see two of those Herbig-Haro objects. So there's probably, well, there most certainly is a forming star somewhere in the center of this little Bach globule or cocoon. And you can see the jets of material blasting outward. You can even see the bow shocks from them too. And you can see another one down here with the two jets coming out. Here is another example of this. This is Herbig-Haro object HH212, taken by the ESOs, that's the European Southern Observatory. This object lies in the constellation of Orion in a dense molecular star-forming region, not far from the famous Horsehead Nebula. The star at the center of this object is indeed a very young star, at only a few thousand years old. Its jets are remarkably symmetric, with several knots appearing at relatively stable intervals. So the star is actually right here in the center. It's blocked, though, by what we assume to be the protostellar disk. You can actually see kind of the disk here. So there's a disk of material surrounding the star that's probably blocking out the light of the protostar. But you can definitely see its two jets and pushing through all this interstellar medium. The stability here suggests that the jet pulses quite regularly and over a short time scale, maybe even as short as 30 years. Further out from the center, large bow shocks spread out into interstellar space, caused by ejected gas colliding with dust and gas at speeds of several hundred kilometers per second. One more. This is HH24. A celestial lightsaber does not lie in a galaxy far, far away, but rather inside of our own galaxy, the Milky Way. It's inside a turbulent birthing ground for new stars known as the Orion B Molecular Cloud Complex, located 1,350 light-years away. Shock fronts developed along the jets and heat the surrounding gas to thousands of degrees Fahrenheit. The jets collide with the surrounding gas and dust and clear vast spaces. Just below the cloaked star, a couple of bright points of young stars are peeking through. So here's the star, and just below them you can see some new stars down here. But this jet looks to, well, in this case, looks to have punched holes in the material around them, right? Look at these two big cavities here around the jets. So presumably this forming star and its jets punched holes through the material. So quite a fascinating event. So let's just end this fairly brief discussion on how these jets might form. This is not set in stone yet, but this is the leading theory for how this works. The most promising models for explaining the jets rely on magnetic fields to link the angular momentum of the protostar's disk to the outflowing gas in the jet. Magnetic field lines passing through a protostellar disk get twisted into a rope-like configuration because of the disk's rotation. And this twisted field may help channel jets of charged particles along the rotational axis. Together, winds and jets can help clear away the cocoon of gas that surrounds a forming star, that thus reveals the protostar within. So the idea is that material is flying away from the protostar because of radiation and stellar wind. But because of these magnetic field lines getting twisted around the rotational axis, it kind of channels the material to stay inside of it or along those field lines. So as a result, the material gets blasted away in these jets in a fairly energetic process. And it's so energetic again that it can clear away the material around it, revealing the star. Well, protostar. We haven't gotten to actual stars yet. So I think this is a good point to stop and break up the lecture before we go into the other half of this discussion on protostars. So this was just a discussion on the formation of them. So we talked about how we got up to a protostar by talking about the collapse of different dense regions in space. So what we're going to do now is look at the evolution of a protostar. So we're going to take a look at what happens to one of these protostars all the way up until it becomes an official star, defined by both being in hydrostatic equilibrium and having nuclear fusion in its core. So that will be the discussion for our next video, and then we will finally be able to talk about the lives and eventually the deaths of stars following that. As always, thanks for watching, and have a great day.